Now oftentimes we'll define a vector as it exists between 2 points. The general form for our vector f would be a sub x minus o sub x, comma a sub y minus o sub y, comma a sub z minus o sub z. As we see on the figure to the right, a sub x is going to be the point of termination of f sub x, and o in its x component is going to be our point of origination. So a sub x minus o sub x defines the magnitude of f sub x that's acting along the x direction, which would have a direction corresponding to I hat. A sub y minus o sub y is going to take our point of termination minus our point of origination of our y component of our force vector, which defines the magnitude f sub y, and j hat would describe its direction. Lastly, a sub z minus o sub z is taking our point of termination minus our point of origination that defines f sub z, and the direction would be denoted by k hat. Now in this formulation, o sub x does not always have to be the origin. It just depends upon where our vector originates. Now, calculating the magnitude of a vector is rather easy. To take the magnitude of the vector, we'll denote it as f, in italic, which means there is no directionality associated. F is going to be equal to the magnitude of our vector f. And this is equal to the square root of the sum of our squares. That is, we'd have the square root of f sub x squared plus f sub y squared plus f sub z squared. Now we'll get into the finer details of calculating the magnitudes once we have a better way to describe the angle between two vectors, and we'll see how our I hats, j hats, and k hats drop out in this calculation. But until we get to that point, we will not worry. In example 2, given our following vectors, let's determine the magnitudes. And we recall we are going to have to use significant figures. In our first example, we have a vector f, described as 4.20 I hat plus 3.8 j hat plus 5.30 k hat. To calculate the magnitude, we're going to have the square root of the quantity 4.20 squared plus 3.8 squared plus 5.30 squared. Now when we take 4.20 squared, we'll express that number in 3 significant digits. When we take 3.8 squared, we're going to express that resultant in 2 significant digits. And lastly, when we take 5.30 squared, we're going to express that result in 3 significant digits. Now, when we add these terms, recall our rule for addition that we are going to take our least accurate answer that defines the accuracy of our significant digit. And once we do that, we're able to take the square root. Thus, the magnitude of our vector will be equal to 7.7. If we look at example 2, to calculate the magnitude, we will take the square root of 8.00 squared plus 3.00 squared plus 4.2 squared. Now when we take 8 squared, we're going to express the result as 64.0. When we take 3 squared, we're going to express our result as 9.00. When we take 4.2 squared, we're going to express that result in 2 significant digits. Then when we sum these 3 terms, the least accurate input is going to define the accuracy of a result, and then we'll take the square root thereof. And we find the magnitude to be 9.5.